It is my pleasure to introduce a good friend of mine, Bob Whitty. And I have known each other since the mid-90s. When I was down in Colorado Springs, we served on the board of Pikes Peak FM Association, and he was on the cabinet staff when I was section manager as technical coordinator. Completely revamped that program and made sure we had people that were attending swap fests and helping people out with technical issues all over the state of Colorado. And he's a good friend. The avid VHF contester and Summits on the Air kind of guy. And I've always looked to him to keep me honest with VHF contesting and things of that nature. He was a vice president at Hewlett Packard, which became Agilent, and has written a couple of books on test equipment. So he's pretty well known, not just in amateur radio, but in the industry. And it is my great good pleasure to introduce him. Would you please welcome Bob Whitty?
Hey, thanks. All right, we're good with the audio. And John, I'll get you that file in a minute. Let's see if we can get this thing to come up. Yeah, all right. Well, thanks, Jeff. I appreciate the introduction. And I do like to talk about test equipment, and this will be a fun opportunity today. Yeah, Jeff gave you some of my technical background. I am an electrical engineer by training. I worked over 40 years in test and measurement. I'm still doing some I'm retired, but still doing some consulting. And lately my ham radio interest has been a collection of like VHF, radio, mountains, and exploring. And so that fits really nicely with SOTA, Summits on the Air, and Parks on the Air. And I do like to write stuff. I write for most of the major ham magazines, and I've written 2 books on test and measurement. Here's what I thought we'd do today. I've done this talk a number of times, but one thing I shifted this time is a little less emphasis on like the basic stuff like multimeters and SWR meters, and more emphasis on vector network analyzers and oscilloscopes, and I'll do a little bit on spectrum analyzers as well. And the reason for that is those things have gotten a lot more affordable in the last 5+ years. Used to be, if you wanted a spectrum analyzer, you buy something new, it's $10,000 maybe, or maybe you go out on the used market and you find something more affordable, but it's kind of a high ticket item. Same with scopes, same with VNAs, but that, as we'll see, that's really changed, right? There's all these low cost products that for ham use, I think are pretty darn good. So we'll be talking about that. Got a couple breaks in here, so we'll try and break it up, and feel free to ask questions as we go along. So just want to start with why do you even need this stuff, right? And I always say that the problem is with electricity, you usually can't see what's going on, right? You can't observe the electrons, the current or whatever. And so we have all kinds of cool gizmos like this that let you hook up to a network and see what the situation is. So I call that Bob's first law of electronic measurement. And then the second law is, if you do start seeing electricity, it's usually bad. Something sparking, lightning's crashing, whatever. So that's the second law. Here's a picture of electromagnetic spectrum. And of course, it goes all the way from DC, right? So direct current has 0 frequency, all the way up to gamma rays. Of course, we're interested in the radio portion of that, right? So it's going to be DC up to, I don't know how many gigahertz we want to talk about. In fact, let's see who has the highest, who's successfully completed the highest ham radio QSO. I've done up to 10 gigahertz. Anybody been higher than that? Doug says yes. What have you done, Doug? 75 gig. All right. That's pretty high. Pardon? 110 kilometers. Okay, very good. As most people is probably, up to maybe 70 centimeters, pretty common, right? That the 440 megahertz band. And so from a measurement point of view, it's useful to kind of break this down. There's at the bottom we got DC, AC power is about 50 to 60 hertz depending on where you're at. And then you get into the audio range, and then low frequency 30 kilohertz to say 300 kilohertz, then into medium frequencies and on up through HF. And this makes a big difference because we have different test equipment that can work at different frequencies. So I wanted to emphasize that. So here's that same chart expanded out a bit. And I think the most common piece of test equipment's got to be the digital multimeter, right? So got a few examples here. Who's got a digital multimeter? Everybody, right? Joyce, you can raise your hand too. So that's my wife, Joyce, K0JJW, along with me today. So of course, digital multimeter is limited in frequency, right? It does well at DC, it does AC power just fine. Most of them will kind of work into the audio range, and then they'll tend to poop out after that. And I'll go ahead and pass this one around just as an example. Let's see. So let's to pass it around, let's go all the way back on this side and then take it back up to the front on the other side. And then the other tool that we use a lot is the SWR meter. And I've got a few of those as well. And those start working at kind of RF somewhere, and then they'll go up in frequency. Of course, depends on the model. You have to pay attention to what frequency they're good for. And also antenna analyzers are real common as well, right? They become pretty affordable. We'll take a look at oscilloscopes a little more deeper later. And here we're looking at time domain measurements, of course. So that's voltage versus time is the key measurement. And those things pretty much cover the whole gamut. I mean, they work at DC and they go way up in frequency, depends how much money you spend. But 100 megahertz is pretty common for a scope, but 500 megahertz or up into the multiple gigahertz region is also very common or very obtainable. And so I use the term time domain there. So this is a picture of time and frequency domain. So when you look in the time domain, you're kind of looking that way. You got amplitude, really voltage versus time. And so that's one view of a signal. And then if we'll talk about the frequency domain in a minute. Frequency domain, I'm looking at it as amplitude versus frequency. So I'll see what the spectral components are. And it's the same signal, just two different ways of looking at it. And pretty important. Both of those are really important when we make measurements. So frequency domain, we get into a couple of different pieces of equipment, primarily the vector network analyzer or VNA or a spectrum analyzer. And those will typically start maybe not all the way down to audio, but kind of in the low frequency range. And then depending on how much money you spend, you can go up to multiple gigahertz. Somebody needs to mute there. We're getting a little bit of Okay, so that's a little bit about the different pieces of equipment and how, where they're going to work frequency wise. And then we'll just a quick touch on measurement technology. You know, all measurements contain some error. So there's always, so the issue is not whether there's error in the measurement, it's how much error there is. And so here's some terminology we'll use to describe that. Accuracy means closeness of the agreement between measurement result and the true value. Uncertainty of the measurement, quantify how much it might be off. Repeatability is really important because even if we're off in our absolute measurement, if it's repeatable, that can really help us because we can see how things change over time and make judgments based on that. And then resolution is always a factor too, because if I'm trying to improve something, depending on how fine of a resolution I have, I can see small changes in my measurement. A little bit of review on decibels, because we use dB or decibels a lot in the measurement world. Main reason is we have a large range of signals, right? We've got, you know, maybe a kilowatt RF signal all the way down to just a fraction of a microvolt at our receiver. So decibels help us handle that. So decibels are really defined in terms of power ratio. Now we got to do a little bit of math here. So it's 10 log of the two powers. And so examples are if one power is 10 watts and the other one is 5, I do 10 log of that, I get 3 dB. If I reverse those two, I get the same answer with a minus sign, right? I get minus 3 dB. So here's some other examples. Another example, so we can do a factor of 10, 100 watts or 10 watts versus 10 watts, that's a 10 dB difference. Or if I flip the two, it's minus 10 dB. And so we have these two kind of rules of thumb we can use. The doubling the power is a 3 dB change, right? And 10 times the power is a 10 dB change. Now you can also use decibels to refer to voltages. And you have to be a little bit careful when you do that because usually what we assume is that the resistance or the impedance didn't change. So here's a little bit of math again. So we'll start with power, P1 or P2, and we'll stick in V squared over R, right? Power equals V squared divided by R. And then if we assume we have the same resistance in both powers or voltages, then the resistance drops out of the equation and we just end up with not 10 log of the ratio, we end up with 20 log of the ratio. So some examples there, take 10 volts, divide by 5 volts, so that's a factor of 2. In voltage, we actually get a 6 dB difference in decibels. And then if we look at 100 volts and 10 watts, and that, sorry, got a typo in there. That should say, yeah, I got watts everywhere, don't I? Look, pretend that those always say volts. So 100 volts divided by 10, you get 20 dB. So you've got a factor of 2 difference in there compared to the power when we do changes with power. So handy rules: twice the voltage, 6 dB. 10 times the voltage is 20 dB. Make sense? A lot of people are real familiar with that. Some it might be new. Okay, so what about the multimeter? Goes by a bunch of different names: volt ohm, milliammeter, VOM, DVM, digital voltmeter, DMM. Most of the products we have these days are DMMs, right? Digital multimeters. Typically, it's a voltmeter, ammeter, ohm meter combined into one instrument. It'll do AC and DC measurements. And then a lot of these, like the one unit I passed around there it's a pretty nice little Max Tech meter that has all kinds of stuff: diode test, continuity, frequency, even temperature. Can come in a bench or a handheld form factor. And these days, it's going to be mostly digital meters, but there are still, good analog meters out in the world. In fact, there's just a ton to choose from, right? In fact, I have this problem. These very affordable meters show up on the market, and I think, I need to get my hands on one. And so, I'm out there on Amazon going click, click, click. Next thing you know, it shows up like the next day on my front porch. And so I accumulate way too many of these, but they're always, I'm always impressed of what is actually available. So quick guide to buying a DMM. First of all, what? You don't have a multimeter? What the heck's wrong with you? These days, I'd say just buy a digital meter. I don't know. I don't mess with analog ones anymore. Life's too short to try and read that meter. You're going to have AC or DC volts, AC volts, resistance, and current typically. Look for a minimum rating of the 600 volt Cat 2. Almost all of them have it. But that's a good kind of a safety factor to be looking for. And then there's all these other features. Whenever I say don't buy an analog one, people say, well, wait a minute, if I want to follow a trend on a meter, I really want that. Well, you can on these better digital meters, you can get this analog bar graph thing that'll help you with that. So if that's important to you, that's one way to do it. And here is the classic Simpson Model 260. They still make this thing. I think it's like $300 or something. It's pretty expensive, but that's your classic, right? Here's one off of Amazon, $14 delivered to your door, and it pretty much does what you need. And then I've not been a huge fan of the clamp meters, but I had to buy one because you can take that and for current measurements, you can clamp onto a wire. So I'll pass this around. It does everything else too, I think. And how much is it? $28. Now this one, the clamp feature is only for AC current. It doesn't do DC, but there are ones available that'll do DC. They're a little more expensive, but also available. Okay, so that's kind of a quick run through on the meter thing. The other common piece of equipment is standing wave or is SWR meters, so we need to talk about standing wave ratio a little bit. SWR, really more properly called voltage standing wave ratio, VSWR, and so you hear people refer to it as VSWR. What's your VSWR? And really it measures the match between the source and a load. Perfect match, of course, everybody knows SWR equals 1, right? And then anything greater than 1 is less than perfect, and SWR is always greater than or equal to 1. So here's kind of the basic measurement. You've got some kind of a forward voltage coming from, let's say, a transmitter, transceiver, and we'll get some reflection back off of that, and we can calculate the SWR based on those two things. And so you do get this standing wave effect, depending on how bad the mismatch is. And so people will talk about, oh, my transmission line or my antenna system is flat. That's what they mean is there is no standing wave, that it's SWR equals 1. But in the general case, it's going to have these peaks and valleys. And that's where the whole concept of standing wave ratio came from. But to me, I think I almost wish we hadn't adopted the term SWR, because it's kind of like it's talking about what's going on the transmission line. But really, I think what we really care about is what's the impedance, and what's the impedance looking into an antenna system, We'd like it usually to be 50 ohms. There are cases where you don't want or need that, but kind of the general case. And so I always tell people that SWR is all about impedance matching. So don't get hung up on waves and standing waves and all that. Think of it as what's my impedance. There's a number of ways to describe that. You know, I can have you know, the impedance is some resistive value plus J times the reactive value if you're doing complex impedance. Simple calculation, if the impedance is real, if it's just resistive, then you can just take the ratio of the impedance over Z0. So for example, what's the SWR if the load impedance is 100 ohms? Just take 100 divided by 50, our characteristic impedance, and we get 2. So pretty easy to deal with. Now there are other ways to describe this impedance matching behavior, and electrical engineers use these a lot. I'd say, like in most of the work I've done, you know, in test and measurement, we hardly ever hear SWR. It's always about reflection coefficient, which is just the ratio of the reflective voltage over the forward voltage, or more likely return loss. And that's where you take the 20 log of the reflection coefficient. And that's really commonly used. It's a more precise kind of way to talk about reflection. A little bit more about SWR. Yeah, the perfect match is 1. It's always greater than or equal to 1. Down at the bottom here, SWR less than 2 is usually considered a pretty good match, right? SWR greater than 3 is poor, and if it's greater than 5, we'd call that very poor. So here's a table of SWR, reflection coefficient, and return loss, so we can kind of do a little comparison. So if I have a 50 ohm load, what's the SWR going to be? 1, right? It's a perfect match. Reflection coefficient? 0, because nothing's going to reflect. Let's see. Does our, yeah. So our standing wave ratio is 1, reflection coefficient 0, and then return loss is going to be infinite. So basically, think of return loss as there's some forward voltage and something's coming back, and it's the in decibels. What's the return loss is the ratio of those two expressed in decibels. If nothing's coming back, then return loss is infinite. So how about 150 load? SWR is what? 3, yeah, 150 divided by, we're assuming characteristic impedance of 50 ohms. And so reflection coefficient is going to be 0.5, and then return loss will be 6 dB. So you're seeing 6 dB loss on the reflection that's coming back. And one more. What if I have an open circuit out there? SWR is going to be infinite, right? Yep. And so reflection coefficient is going to be 1. Everything's coming back to us. And same with return loss. 0 dB return loss says there's no difference between the forward voltage and the reflective voltage. Okay, so how do we measure this? Well, we measure with an SWR meter, of course, right? I've got one here made by Diamond. I'll pass this around in a second. You know, the SWR meter is inserted in line. We're going to use the power of the transceiver or the transmitter to stimulate the antenna system and see what happens. And these days, particularly on HF transceivers, the SWR meter is often built in, which is really, really nice, right? You've always got a built-in meter there that's telling you what the radio is experiencing. Here's what's inside one. There's a directional coupler or bridge that extracts the forward and reflected voltage and forward and reflected voltages. And then there has to be some kind of calculation. It might actually be a microprocessor that makes that calculation, or there's some meter techniques that can be used. And then that gets displayed on the meter. Pretty straightforward. So here's this diamond. Actually, this is the SX600. This one goes up to UHF. The one on the slide goes up to 200 megahertz and has a number of different power ranges. Down on the lower right, it's got a switch that says power, cal, or SWR. And the way it handles this calculation of the of forward voltage and reflected voltage to SWR is you set it on cal, and then you turn the knob there and you set it to full scale. And so that calibrates the measurement, and you flip it to SWR, and the meter will, based on how the scale is set up, the meter will read out in SWR. Pretty common approach. Here's a Comet SWR meter, and it has two scales, really 2 meters built into one, and one is showing you the forward voltage, one is showing the reflected, and where the 2 meters cross, you can read out what the SWR is. So that the calculation is handled by the meter layout. Pretty clever approach. And then here's kind of a high-end watt meter, SWR meter. You can set it has I think it has a remote head you can put in line, and then this thing reads out all the time in real time either what the power is or both power and SWR, so you always know what's going on. So it's doing a calculation with a microprocessor inside. I came across this little guy, another one of those Amazon gems, right? Tooling along on Amazon. It's like SWR power meter for $36. Now it's really VHF, UHF only. And I don't think it's super accurate, but I've checked it against some other meters. I'd say it's useful. And so really tiny portable things. So I'll throw it in my backpack for soda activity or whatever. If I ever get confused about, do I have any signal, I can pop that guy out. And then, so moving on from SWR meters, antenna analyzers have become quite popular and pretty affordable. And there's a bunch of them out there, right? And the key thing about the antenna analyzer, this is a classic, right? This is the MFJ. Let's see, that says 259B. This one says it's a 259. Okay, same one. And it's been around for a while. I don't know when they introduced it, but it's still pretty popular. And it has a signal generator inside, so it's going to stimulate the antenna system itself, and then see what kind of signals are coming back. And so you pretty much just dial in the frequency you're interested in. It's going to tell you what the SWR is. And it's got a bunch of different settings. You can look at SWR, you can look at return loss, impedance, reactance, resistance, whatever you're interested in. $250. So it's kind of, I think about the hobbyist market. We spend $1,000 on an HF transceiver, right? Maybe more. And so for test equipment, if you're well under $1,000, I think of that as the within the hobbyist or the ham radio market. So certainly anything under 500 starts to look attractive. 250's pretty affordable. So here's what the meter displays. I'll go ahead and send this on around. So it's reading out the frequency and the SWR, and in this case is set on resistance and reactance. They also give you a meter down below in case you want to kind of spot trends as things are moving around. Yeah, a few tips on this thing. This is going to be true of all SWR meters. They're really best near 50 ohms. They may tell you that the impedance is 5,000 ohms, but that's not going to be a very accurate measurement. It's going to be really good at 50 ohms, which is probably where we're most interested anyway. Don't use in a high RF environment. Sometimes you'll have your meter sitting there and it'll start flopping around because there's some transmitter coming on over here, and you're going, why is this signal, why is the reading changing? It's because you're getting interference. The input circuitry is pretty sensitive, so you can blow these things up. Like don't hook your transmitter into it and transmit. That's a bad day. They always say discharge antennas before connecting. Same issue. Don't get static charge coming in. No external voltages, and don't overinterpret the results. All these SWR measurements don't really tell you how well your antenna is working, right? That SWR into a dummy load is perfect in it, but it doesn't radiate at all. So it's really just all about that impedance match. So just keep that in mind. Here's another one I have, the Comet CAA 500. I think it's a higher quality and simpler to use antenna analyzer. And then there's a whole bunch. I mean, there's a lot of good antenna analyzers out there, and what they're doing now is they give you that plot of SWR versus frequency, and that's really handy to see what's going on, right? And hopefully when you hook it up to your antenna, you see a nice resonance. You go, okay, that's where my SWR is best, and maybe the frequency is a little off and I need to tune it or whatever, but it gives you a good visualization. Here's another one. This is got this one here. They call this a vector impedance analyzer. Okay. There we go. Now it's only good for VHF and UHF. So its low frequency is at 137 megahertz, and it goes all the way to 2.6 or 2.7 gigahertz. So pretty nice. And so it's a nice meter, about $160 on eBay. I'll pass that one around. Again, these are really examples, right? There's just so many to choose from out there. This is that same meter, and it does have the graphical display, so you can see over on the right. I've got it hooked up to an antenna, and I'm looking at the SWR versus frequency, and it's showing me that usual curve where the SWR is really good at some frequency, and then it degrades as we move off of that frequency. Okay, I think that's it for this first section here. What kind of questions do you have, Doug?
The question is worthy of a microphone, but I loved your little tables and mathematical calculations. And usually when you put formulas in a talk, you lose half your audience, and yours were spot on. But we looked at where my question is leading towards is a lot of us will have these tools and we want to see, is our antenna system and cable system intact? And that's what you're measuring. But some of us The ideal is you have a very short feed line, very low loss. But some of us have very long cables with 1, 2, 3, 4 dB of loss. And when you get to that and you put one of these meters with a lossy cable in between, I suspect you see where I'm going.
Yeah.
It's going to
yeah.
skew these meters. You might comment on that.
Okay. Yeah, actually, I had a couple of slides on it and I pulled that, but, yeah, what Doug's getting at is, again, you're looking at the measurement is occurring wherever the SWR meter is. And there's a difference between measuring the end of your coax, like in your ham shack. Let's take the typical case, right? You're in your ham shack and you hook up the SWR meter or you hook up the antenna analyzer. So then there's a coax that goes all the way out to your antenna. That's going to vary on your installation, but let's take an extreme case. Suppose you have crappy coax. Well, shouldn't call it crappy, right? Higher loss coax, like RG58, right? So I've got 100 feet of RG58 and I'm using it at 440 megahertz. It turns out there's quite the loss in that length of cable. Yeah, I think maybe even more. So, yeah, so there you go. Let's say it has whatever it is, it has 6 dB loss. So my signal going down to the antenna is gonna degrade by 6 dB, and let's do it in terms of power. So I'm going to lose not just half the power. I'm going to lose 3 dB and 3 dB, right? So it's half the power and half the power. So it's 4. I'm going to lose 4x the power, or it's going to be 25%, right? That's on the way down. Now, if there's a reflection at the antenna and that signal comes all the way back, it's going to lose that amount again. So one phenomenon is I sit there with my SWR meter and I go, the SWR looks great, because all the meter is seeing, it's got some forward voltage going down and hardly anything coming back because of all the loss in the cable. So really the answer to that is you need to crawl up, or you need new coax, you need different coax, I think. But you crawl up to your antenna and you make the measurement, with just a really short cable. Or at the very least, just be aware that kind of phenomena occurs, that cable loss makes SWR look better than it really is.
So I don't know if my mic is still on. So if you have a 6 dB loss cable and your antenna actually accidentally is disconnected, you're going to see 6 dB up, 6 dB back, which is 12 dB return loss. And just doing that in my head, what's that, about 1.4 to 1 VSWR? You're going to think you've got a decent antenna up there when you have an unterminated piece of cable. Yeah, you've got a great chart for that.
I'm going to use my table here.
There we go.
What'd you say, like
So,
return loss?
Let's use the 13.98 or the 10.46. So you're going to have somewhere between 1.5 to 1 and 1.8 to 1 VSWR without an antenna connected.
Well, your meter is going to read that.
Yeah.
At the end of the
That's
coax.
what it's going to claim when you really have nothing. And if you then connect to this really poor cable, a really poor radiating antenna, you're going to get some energy radiating, but it's not a lot, and it's reflecting back. You're going to think you've got a very good antenna and cable when you don't.
Right.
And I was doing this for work yesterday, and one of the guys in the room here, we were sweeping cables, and I said, well, let's make sure we take this into account, because we're at the end of 100 feet of hard line, and there will be some loss in that. So a really lossy piece of cable is a great antenna tuner if your antenna isn't resonant.
Yeah, antenna tuner. Yeah.
And I use that term loosely.
I've even run into cases where people are going, I need a good load to put on put on a transmitter, and they're going, I don't have a dummy load with me. And it was high enough frequency. We just got a really long piece of coax and put it on there, knowing that reflection, it's going to be reflection at the end, but the loss in the coax was so long, it just wouldn't, it was good enough for our dummy load. Yeah, hopefully, yeah. Okay, thanks for that, Doug. Other questions? Yeah.
Thank you. One of the slides mentioned that with the time domain, you could determine where you might have a fault in the coax.
Right. I kind of skipped over that. This one, probably this one.
Yeah.
So, yeah, so these, in fact, we'll touch on this a little bit later as well, but these antenna analyzers will often include a time domain reflectometer mode, TDR. And there's a couple different ways they can do that. They could actually put a little pulse down the cable and see what kind of reflections come back, or they may just use the frequency domain information and do a Fourier transform on it to get back to the time domain. But basically the idea is I can look at my coaxial cable in time. And so imagine that a pulse goes down that cable and you have a bad connector somewhere. You'll get a little bit of a reflection off of that comes back. And then further on down, you may see, another reflection, and then when it gets to the antenna, you may see a small reflection off of that. And so that gives you this picture of what's really going on in your antenna system. And so, like if you did have a fault, you could actually, you have to take into account the velocity of propagation through the coax, but you can figure out that, hey, I've got a problem about 50 feet into my coax, and you go outside and okay, 50 feet, and you find out there's a squirrel chewed through your coax, or some kind of damage occurred. So that's a pretty handy feature. So thanks.
Thank you.
Other questions?
Hello. Yeah,
On
your
that
1
one?
meter. Yeah, 137 is the bottom.
Well, yeah, I don't know about 137, but they obviously designed it for VHF, UHF, and a little bit into the microwave range kind of thing, right? So there's probably a cost trade-off. So for me, this is like an awesome meter. For somebody that's on HF all the time, they're like, I can't use it, right? So always have to pay attention to the frequency coverage of the antenna analyzer. Same thing's true on the SWR meters. They have a a specification on what frequencies it's good for, and particularly the directional coupler or bridge that's inside is designed for a certain frequency range, or it's optimized for a certain frequency range. Okay.
So if we're online, do we just sing out questions or do we type them in the chat?
Just come off mute and ask him.
Yeah, Bob, Greg Liverman, K0MGL.
Yeah, hi, Greg.
If I have that legendary crappy coax, how do I determine that my piece of coax is not good? Do I use this TDR technique?
I didn't mean to insult your coax, Greg.
That's okay.
Yeah, good question. How do I check out a piece of coax? So the TDR approach is probably good. What I've typically done is I'll go ahead and make a let's call it a through measurement. In other words, I'll put some kind of signal into one end of the coax and then measure what's coming out of the other end and see how much loss I have. It's typically what I'll do. And it turns out a VNA would be a really good piece of equipment to do that with. Now, if your coax is already strung up a mast and it's kind of all attached, that it's going to be hard to get up there to make that measurement. But that's maybe where the TDR comes in. Yeah, Doug?
One suggestion, if it's already strung up the tower or out and you can get to the attachment point, but it's not easy to put a meter up there, either open the cable or put a short up there and then run your return loss measurement. And the return loss of a short or an open, because everything's going to reflect back, is going to be twice the loss of the cable. So if you have a
I like that.
3 dB cable, short it at the far end, take your measurement, and if it comes back 6 dB, you've got a 3 dB cable.
Yeah.
Do that all the time
like
because
that.
you don't want to undo a hard line or RG8 from your tower, but you can maybe get up there and put an opener, or better yet, for that measurement, a short.
Yeah, that's a really good idea. So did you hear that, Greg?
I did. Thank you very much.
So that makes me think of a couple other things. Usually a DMM is not good for making these radio frequency measurements, but when I'm installing coax, sometimes I'll use that as a really basic continuity test, right? So you take the end of your coax and with nothing connected on the other end, and I probably just crimped or soldered the connector on. I don't trust my ability to do that. So I get out the DMM and I put it on ohms, and I want to see an open circuit between the shell and the center conductor, right? And then I can do things like, okay, do I have continuity all the way to the other end? I can bring the other end over and I can check for continuity between the two center conductors, right? I want that to be low ohms. And then same thing with the shell. That's a pretty basic DC kind of test. And then some other things I've done is if I'm skeptical of my antenna system and something's not quite right, I'll go ahead and put a 50 ohm load on the other end. And so like let's say I got my antenna analyzer and I'm going, SWR seems too high. Is it the antenna? Is it the coax? Well, I'll put a 50 ohm load on the other end of the coax. And if the SWR looks good, close to 1, then it's probably not the coax. If it's bad, if it's high, then I start looking at the coax. And then the thing to watch out for is sometimes the antenna can mislead you, particularly on that DC test. If you leave, I've had people, say, hey, I got a real problem with my antenna system. I was sitting in my ham shack and I didn't think things were right. So I got my DMM out and I checked the resistance from center conductor to shell, and it's shorted out. Something's wrong. And then I climbed up to my antenna and I disconnected the coax and the short went away. Well, it's because your antenna is shorted on purpose at DC, right? A lot of antenna designs will be a short. So kind of have to watch out for that. So something else to consider. Other questions? Oh yeah, that's a good one. Yeah. Yeah, Doug mentions that different surge suppressors, lightning arresters. I think whoever named them lightning arresters was an optimist. I've never seen lightning arrested. So let's go with surge suppressor. They have different designs. Some of those are shorted to ground for DC. And so you need to be aware of that if you're out troubleshooting. In fact, that's caused me some serious headaches. I was helping somebody troubleshoot an antenna system at a fire station. I'm getting really strange readings, I'm going, what the heck's going on? And He's like, oh, we do have third suppressors in line. It's like, well, okay, where are those? They're in a box somewhere, and we had to track them down and take that. And sure enough, those were all shorted for DC. So another complication to be concerned about. Okay, how we doing? Okay, I think we're doing good on time. I do want to take a break, give you guys a little bit of a break and set up a few things. Next up will be oscilloscopes, and we'll spend, like 50 minutes or so on scope measurements. Okay, I think we're back, huh? My audio working okay? Yeah, all right, great. All right, thanks, everybody. We will now talk about oscilloscopes. And I mentioned earlier, oscilloscopes used to be this big, expensive thing that not that many people would have access to. And that situation has really changed. So I think they're a valuable tool for ham radio and electronics hobbyists. We'll spend maybe 50 minutes on this. And we'll just start with what is an oscilloscope. So it's all about looking at voltages versus time, right? So you hook up an oscilloscope, got one sitting right here, and I can see what the waveform's doing. And as I said in the first section, we can't see this stuff. We need equipment to help us see what's going on. Oscilloscopes go by a lot of different names, particularly as the digital technologies come in. Usually people just say it's a scope. They might say it's a DSO or a digital scope or digitizing scope. There are analog scopes. Basically, nobody makes analog scopes anymore, but there are plenty of them available on the used market. Sometimes people will call them cathode ray oscilloscopes or crows. I ran into a customer one day. It's like, yeah, we've got a whole bunch of crows in our lab, and it's like, well, I'm sorry, you should probably get them out of there, And finally, I figured out, oh, he's talking about analog scopes. Okay. Sometimes you call them O-scopes, and then there's this one variant that's pretty popular, the MSO, mixed signal oscilloscope. And the idea there is you just add a few basic logic channels into the system so you can hook up to digital signals and see more of what's going on in digital circuits. So those are some of the names. We'll probably just call them scopes. And it's funny, there's been different user interfaces tried on oscilloscopes, but they've kind of all morphed to this, where you have you have the vertical channels, the input channels set up with a couple of scaling knobs, volts per division knobs, and then they have a position knob so you can move them up and down. Usually the inputs are BNCs and they're on the bottom. And then someplace there's a time-based knob, the horizontal scaling, also a time-based position, and then some triggering controls. And then of course there's a lot of things hidden in menus, right? A lot of the more advanced features tend to be in a menu somewhere, but the knobs have always stayed on the front of the, easy access on the front panel, because typically a scope is a very interactive kind of device. I'm probing around trying to figure out what's going on in my circuit, and I'm visually looking at that display, because usually the question is, does the signal look the way I expected it to be, right? So I'm doing a judgment as to, does it look right? And I'm making adjustments as I do that. So lots of knobs, lots of interaction. So who has an oscilloscope in their personal possession? Lots of people. Okay, great. How many of them are, who has analog only? And who has digital? Okay, so kind of a mix, really. Here's a look at the scope's display. Pretty straightforward. You know, there's a graticule. A lot of times we're just making measurements by looking at, you know, how many divisions it is. Oh, I know it's 1 volt per division. So if the waveform is six divisions high, then it's going to be 6 volts, things like that. Very visual. In digital scopes, they always have some measurement aids. So the first one is usually some kind of cursor system where you can move a cursor back and forth on the waveform, and it'll tell you, you know, that peak voltage is 4.2 volts or whatever. And you can also measure time differences. You know, how far is it from this point on the waveform to that point on the waveform, tell you what that time is, that sort of thing. And they have automatic waveform measurements as well. And, you know, that makes a lot of sense. You got all the data. Go ahead and tell me what the answer is. If I might be able to select volts peak to peak, frequency, of course, peak voltage, average voltage, things like that. And, you know, a calculation that's not easy is RMS, right? You can push volts RMS and the scope will figure out what the RMS voltage is. Good stuff. I'll touch briefly on triggering. It's, you know, if you haven't used the scope, it may not be obvious why you need triggering, but like in the upper left here, if you just turn a scope on and it's untriggered and you're looking at some signal, it's just going to wander all over the place because there's nothing that's stabilizing or defining what zero time is or anything. It's just going to keep displaying. So the most simple trigger is just a slope trigger. So here we have the scope is set up to trigger at 0 volts with a rising edge. And so boom, the waveform stabilizes doing that. And I can change that trigger level, right? Usually it's a knob, might be in a menu, usually a knob, and you move it around. It's like, I want to trigger up here, and I can change the slope that I want to trigger on. I can say positive or negative. And then over time, there's been all kinds of creative triggering added to this simple thing. You can trigger on pulse width. You can trigger on, you know, particular logic sequences. There's just a lot you can do. So here's a look at what's going on inside the scope. You've got, and this course is going to be digital. Not going to spend any time on analog today. You've got the front end system, which usually has an attenuator and some kind of amplifier. That's the fundamental input of the system. And then we're going to digitize that. We're going to feed that to an analog to digital converter. And then that's going to go into some kind of storage memory. And then ultimately we'll have to, we'll display that waveform on some kind of display. You know, they're typically LCD displays these days. So up front, the bandwidth of the scope is going to generally be limited by whatever amplifier circuitry you have up there, and the sensitivity. You know, usually these scopes go down to about 1 millivolt per division, that sort of thing. And then inside the acquisition system, the main issues are sample rate and resolution. sample rate used to be a big deal because it was so expensive. If like the difference between a 20 megasample per second A to D and a gigasample A to D was so huge that it's when we were designing scopes, it's kind of like, I'm just going to put as much sample rate as I can afford into that particular product. And it was always a limiting factor. Those days are gone. You know, gigasample A to D converters are quite affordable these days, and you just pop them in everywhere. The other issue is resolution. So that's the number of bits of the A to D. And the industry standard is really 8 bits, because that's about enough resolution to give you a decent display for most applications. But some products are starting to push that now. You'll see them at 12 or 14 bits to try and give a higher quality picture, right? Of course, they have to have a display that goes with that. You're going to need higher resolution display, but kind of low cost scopes tend to be 8 bits. And then the thing I think is actually very underappreciated is the memory size. A lot of advertisements for scopes don't really talk too much about memory, and I think users often don't really appreciate what it does for them. And I'll dig into that a little bit deeper in a second. And then finally, the display algorithm thing is another thing that scope designers spend a lot of time on that people really don't appreciate, because they kind of think, well, all you're going to do is collect up the data and you're going to throw it on the display. But a lot of energy goes into doing this correctly, giving you the right picture, and also doing it very fast. Because like the early digital scopes were pretty sluggish. They're kind of like, here's your next waveform, here's your next waveform. And if you have a very complicated signal that's moving around, that was like the #1 complaint on digital scopes. People said, look, my analog scope shows me exactly what's going on in real time, and your digital scope looks like a slideshow. It's like click, click. So all the modern digital scopes have solved that problem. They make sure that this system has enough horsepower to really make it go fast. Okay, so digging in on that front end, the performance, the bandwidth of the scope is probably the #1 spec on the scope, right? And the way that's defined is 0 dB is going to be the reference point at very low frequency or DC, and then the oscilloscope is going to have a low pass response. And so when that starts to roll off, when it's 3 dB down, that is by definition the scope's bandwidth. And you know, if you haven't been around scopes too much, you might think, well, wait a minute, why isn't it just a really flat line out to the bandwidth spec and then boom, drops right off? And if you designed a scope like that, what you'd find is it'll have tons of ringing in the response. And so anytime you put a fast pulse in there, it would not be a very good picture. So all oscilloscopes have this, it's actually called a Gaussian frequency response that rolls off. And so some of the implications of that, let's say we have a 100 megahertz scope, which is, you know, pretty common. If I put 100 megahertz sine wave in, it's not going to measure that sine wave accurately, right? It's going to be down, I'll say 3 dB. You know, maybe the scope has a little bit of performance margin built into it. Maybe it's only 2.7 dB down or something, but let's just say it's 3 dB down. So your sine wave is actually going to be smaller than you expected. So 100 megahertz scope, it's not really good for looking at 100 megahertz sine waves. Of course, if you know how much it rolls off, you could maybe write that down and compensate for it. That'd be a way to still use it. So what about bandwidth? Let's take, this is a square wave case, so pretty fast digital signal, 100 megahertz digital clock. And on the right side here, we've got a 500 megahertz scope making that measurement. And it looks like a pretty decent square wave. And it's got a little bit of overshoot there, but pretty good measurement. If I measure that same thing with a 100 megahertz scope, I get a sine wave out, right? Because it's taking it's losing all the harmonic content of that square wave. So rules of thumb for this sort of thing. If you're just measuring sine waves, you probably want a scope that has 3 times, the bandwidth should be 3 times the highest frequency you're going to measure. And then for digital applications, we say 5 times the highest digital clock rate. Although probably the best thing to do is actually think about the actual edge speed that you care about. And you can look up the specification on the scope for its rise time and have that rise time be much smaller than the actual edges of signals you're trying to measure. So here's just a little bit on bandwidth, sample rate, and memory depth. Because so we said bandwidth is the key spec, sample rate is right behind it, and then memory depth, I think, is third. So typically, we're going to have some kind of input amplifier that's going to set the bandwidth. Then we have the analog to digital converter. So that's the sample rate, F sub S. And then the memory holds a certain number of samples. So I called it K sub M here. So I think most people know that these days. Mr. Nyquist says your sample rate must be at least 2 times the highest frequency or 2 times the bandwidth of your scope. And actually, these days scopes usually do 4 times or maybe up to 10 times. So sample rate's really not a big issue anymore. The thing that's still a big issue is time capture, because ideally I'd like to capture at my highest sample rate all the time, no matter where my settings are. And so for example, so here's the equation for that. The time captured is my memory depth, K sub M, times 1 over the sample rate, right? The sample rate, if I take the reciprocal of the sample rate, that gives me the sample time, the time between each sample. So that's my equation that relates time captured and memory depth and sample rate. So let's just try a number. Suppose we want to capture 100 milliseconds, which typically a scope has 10 horizontal divisions. So that'd be 10 milliseconds per division. So that's not real fast. That's actually the scope is kind of set on the slow side, but there could be really high frequency content in that waveform. So I want to be able to sample as fast as possible. So say I have a gigasample per second, A to D. How much memory depth do I need? K sub M equals E times F sub S is, see what I do there. I did a little bit of algebra here, right? So I'm trying to solve for K sub M. So I took F sub S over on that side. So 100 milliseconds, gigasample, I need 100 megasample memory. And a lot of scopes don't have that much memory. And the way I think of it is you can't have too much memory because you never know how long a time you really want to capture. And you'd always like to have that sample rate stay at its maximum. So what do scopes do if they can't store all that memory? There's a bunch back in the early days of digital scopes, they just threw samples away. They're like, you turn the time base down to a slow speed, the scope would sample at a lower rate. these days, they do some processing right here to be smart about which samples they keep and store. Then they do some processing back here to make sure the waveform looks right. But anyway, memory depth, lots of memory depth is good. Let's see, scope inputs. We'll talk about VNAs and spectrum analyzers. Those later. Those are usually pretty sensitive inputs, as in you can blow them up if you aren't careful. Scopes are pretty rugged. Damage level is usually spec'd at 150 to 300 volts RMS, somewhere up there. It's a 1 megohm input, so it's inherently high impedance. And then it does have some parallel capacitance in there that will affect the high frequency measurement. So typically it's like 13 picofarads. And then the higher bandwidth scopes will often provide a 50 ohm input. And so that's usually selectable, right? You say, I want to be 1 megohm or I want to be 50 ohms. If you're using the 50 ohm input, you need to be pretty careful because they're typically more sensitive and it's pretty low impedance, right? So if you put 100 volts into 50 ohms, that's a lot of amps, right? So so the 50 ohm impedance is more fragile typically. And then economy scopes usually don't have a 50 ohm input, but if you want to do a 50 ohm measurement, you get yourself one of those feed through terminations that has 50 ohms inside and put that on the scope input. Those things have some damage levels as well. Typically they'll handle like maybe 1 or 2 watts. So you want to be careful how much power you put into those. Kind of the standard probing technique. These scopes come with a divider probe, 10-to-1, and the reason for that is a divider probe can compensate for this input capacitance on the scope. So here's the input to the scope with that 1 megohm and small capacitance. And if I have the circuit is the divider probe out front, and you give up signal, you're losing, because of the voltage divider in there, you're losing a factor of 10 in signal, but it actually reduces the capacitance at the probe tip by quite a bit. So you can make, really your quality measurements are going to be made with a divider probe like this, the higher frequency measurements. These are passive. There's no transistors or amplifiers in there. There are, for higher performance scopes, there are these things called active probes that have little amplifiers built into the front of the probe. Of course, they get pretty expensive, but if you're making measurements at 10 or 20 gigahertz, you're probably going to have an active probe. But for our typical ham radio stuff, you're probably not doing that. Let's see. Oh, one thing to be aware of is on a scope, this is true of like 99.9% of the scopes. There are a few specialty scopes that don't have this problem. The scope is inherently tied to green wire ground. So the shell of this BNC is connected to the outlet green wire safety ground. And so that means that this little ground lead is also connected there. So when you make a scope measurement, you don't want to be putting this thing on like a 50 volt DC signal, because you'll basically ground out your circuit. Now people do things like use an isolation transformer, cut the green wire ground off. I wouldn't recommend that, and your surviving spouse probably won't appreciate that either. So I made that neutral. I was going to say wife, but I said spouse. Oh yeah, you do have to compensate these things. There's a little variable capacitor out in the probe, and so there'll be a little. Actually, it might be in this. Yeah, on this one, it's back here. So you get your little adjustment tool and you need to adjust that. And if it's properly adjusted, it looks like, oh, you hook it up to a square wave generator on the scope, which is a calibration signal they always have on the front panel. You hook it up to that calibration signal, it should look like a square wave. If it looks like that, over peaked or under peaked, then you need to go make a quick adjustment. And once you do that, you're probably never touch it again. I did want to show, let's go back here. I do have the scope set up here. I want to show some live measurements. So this is a Keysight scope, 70 megahertz, so not super high performance, kind of a basic scope. And I've got it connected to my Fender amplifier. Now for you Spinal Tap fans, this amplifier only goes to 10. I'm sorry. Does not go to 11. And one of the things that's been happening with scopes is they put more and more features inside the oscilloscope. One of the features this thing has is a waveform generator. And they basically, they had to have a square wave for probe compensation. So they went ahead and said, well, let's put a little function generator in there. We'll do sine waves. We'll do this. We'll do that. Let's see. So this is a sine wave, of course. Let's see if we can hear it. Okay, this is also a hearing test, it turns out. Everybody hear that frequency? Anybody want to guess what frequency it is? 1 kilohertz. You are correct. So now here's and of course my scope controls, right? I can go back and forth on the time base. I can do vertical, all that stuff. And then if I increase the frequency, who knows what the frequency response of the speaker in this amp is, but and this is where it really becomes a hearing test, right? Because judging by the age of the crowd, at some frequency, you will no longer hear this, right? I'm at 9 kilohertz there. Anybody hear it? Yeah, I can't hear it. Anyway. And then let's see, we got some other, like I said, it's a simple function generator. That's a square wave. You can go down in frequency. Oops. Okay, back to our kilohertz. There's a square wave. There's a ramp. So you can still hear the harmonics in there, but they're kind of subdued. There's a pulse, has pretty sharp sound to it. Let's see, here's DC. Anybody hear DC? Too low, I think. And then it also has this noise. Noise is actually hard to hear because it's spreading the energy over such a wide frequency. Anyway, those are all the kind of signals you can look at on an oscilloscope. you don't have to have the Fender amp. That was just for dramatic effect here. Let's see. Let's go back to our sine wave. Okay, so what are we gonna, let's go back to the slides now. Thanks for zooming in on that, Chris. So practical ham radio usage, what are you gonna use this for? Certainly measuring audio signals, modulation, receiver audio, sound card. Anytime you've got some kind of relatively low frequency signal you wanna find and check out. Also digital signals, right? Might be working on a Raspberry Pi. Did that signal really change from high to low the way I expected it to? Serial ports. I2C is a real common serial interface. In fact, some scopes will go ahead and give you special feature sets that'll look at an I2C signal and decode the protocol from that, right? So you don't have to mentally go through and look at every bit and figure it out. It'll tell you what information is being transferred. SPI is very similar. And then you can also monitor transmitted RF signal. In fact, this used to be a common thing, right? You had a monitor scope in your ham station, so you could actually look at your RF signal going out. That, I don't even know if they make these anymore. It seems like that's really faded. But if you had an oscilloscope with enough bandwidth to look at the signal, and you need a connection method, right? And we'll talk about that in the next section. So those are some things you can use a scope for. Anybody think of any other typical things you use an oscilloscope for? A doorstop. Well, now this one, this is so small, I don't know if it's a good doorstop, but if you had a good an old analog scope, boy, those things. Yeah.
Interesting problem here recently that I had bad AC power. And so I spent quite a bit of time with my oscilloscope looking at different power sources as well as uninterruptible power supplies. And you would be shocked to see the waveform coming out of most of those. I had some pretty expensive APC equipment, and it puts out a perfect square wave. It basically goes to plus 50 volts, stays there for 20 milliseconds or 10 milliseconds, drops to negative 50 volts. It is not a sine wave at all. And that creates all kinds of problems for computer equipment, and I'm sure for our transmitters as well.
Yeah, that's a good point. A lot of those are, so the topic is these power inverters, right? Where you create 120 volts RMS from a 12 volt battery or whatever. Some of them are square waves, and then some of them, I think they market it as modified sine. You probably saw some of those, and they're like not quite a square wave. They have like one additional step in there, and you go, that's a modified sine. And then the really good ones actually look like sine waves. You could have a technical session just on power converters. Write that down.
Question.
Yeah, Willem, Willem, ask yourself to do a presentation on power converters.
That you're doing it.
Actually, okay, quick funny story. One time I was in the R&D lab, this is back in the HP days, and we're having a problem with a piece of equipment, and somebody wanted to they said, we should just check the power. Are we getting good power into our bench? And so they looked at the bench, the AC coming in, and it looked like crap. It was all jagged. And we're going, how could that possibly be? And then somebody goes, well, you know what? We've been having so much trouble with the power going off during lightning storms. They installed a big UPS system like 6 months earlier, and nobody really thought too much about it, but so the whole lab was on this UPS system with a crappy sine wave. Yeah.
Could you talk a little bit about using the horizontal input for something other than time? You know, like tuning an RTTY signal?
Yeah. Horizontal input. So there's a mode on, I'd say most scopes, probably pretty much all scopes, called XY mode. And so it takes one of the it may be a special input, or it may use one of the front panel inputs as an x-axis input. So the scope becomes an XY plotter, really. You have one BNC is going to plot the vertical on the vertical axis, and the other BNC is going to plot the horizontal axis. And there's a lot of interesting measurements you can use that for. The kind of the classic one is called a Lissajous pattern, where you take two different sine waves, and if you put them into those inputs for XY mode, it gives you, I don't have any pictures, unfortunately, gives you some patterns. You can tell a lot about the relative frequency and phase of those signals. But then the one that's more ham radio related is you put your RTTY signals in there, and that'll show you the quality of your RTTY modulation. Do you know more about it than that? That's well, you get switching
back and forth, and you can tell by the angle, you essentially see two ovals on the screen, and you can tell by the angle on those, between those two ovals, how well your transmitter is tuned, and how your RTTY transmitter is working.
yeah, the mark versus
Yeah, you want them.
So if they're perfect, it's an X, right?
Right. Yeah, it's
Yeah, actually a plus probably.
yeah, it's two ovals at right angles. And I don't know, you could probably use the same thing for the new digital modes for the Joe Taylor modes, but I haven't tried it.
Yeah, I don't know. Okay, thanks for that. So let's look at some affordable scopes. I just went through and pulled the prices off these, make sure they were current. You know, here you got Keysight and Tektronix are the two big, major T&M players in this space. And they've got, Keysight's got a 50 megahertz scope for like $600, and Tech is slightly lower in price than that. Interesting. I had to update the slide because they've been raising their prices with the inflationary pressure. And then Regal is a Chinese company that I have them kind of in the category of probably the highest quality test and measurement products coming out of China. They're doing a pretty good job, I think. And they're at 100 megahertz scope at $329. And then I was poking around on Reddit and other super reliable sources on the web, and people, there's a lot of buzz about the Siglent scope. See, $339 and 200 megahertz. So quite a bit more bandwidth. And then the Handtech is a 100 megahertz scope, 2 channel at $259. So that, and people seem to be pretty happy with them. They're saying, yeah, it's a good scope. It's working fine. So I have not used those ones on the right. But pretty affordable. I mean, 259 is not quite an impulse buy, but it's, let's see, how much does it, what's the tank of gas in my truck? It's 2 tanks of gas, right? Is that what we're talking about here? So, and then maybe a quick comment on channel count. What you never see, never say never, but you hardly ever see a single channel scope, right? They're almost always at least 2 channels. And the idea is if you have one signal to look at, you probably want to compare it to something else, and you may want to look at the time difference or, whatever. So they're always 2 channel is kind of the baseline. And then, but you can get, 4 channel scopes if you want more, be able to look at more signals. That's kind of the next step up. And then that mixed signal oscilloscope category helps you if you have a lot more digital signals. Yeah.
They're affordable. If you buy a Keysight, it's going to tell you you want to calibrate this thing every year or 2. What have you found for the low end? But you buy a Keysight scope, you don't calibrate it in 2 years, it's probably going to hold. The manufacturing quality is phenomenal. What have you found with the lower cost? Do they hold their calibration, or do they need to be tweaked frequently?
Yeah, I really don't know. I don't have enough
Okay.
experience. It's a good point though, because all your test equipment should be calibrated, right? Because they do drift. And so if you're like an electronics manufacturer, all the equipment on your production line, you're gonna pull that out every probably usually a annual cycle, send it to a cal lab. They check it against standards that trace back to NIST, right? Or your whatever country you're in, and they make sure it's within cal, and they tweak it up to make it even better, right? And so that's part of the process of how do you know what a volt is? Well, there's an official volt sitting in Boulder. That's how you know what a volt is. Hobbyists, I don't think hobbyists ever calibrate. Do you ever send your stuff in for cal? Of course, you're not exactly
Not as often as I have to. My ham stuff, no, I don't send it in for cal on a regular basis. My commercial equipment, I have to maintain. And I'll quite often take my ham equipment, check it to my commercial and say, am I close? Is a dB a dB? Is a
Yeah,
volt a volt? But I just wondered, because sometimes economical is not always a good value. It may be good today, but if in a year the thing is 1 volt is really 2 volts, can you trust it? And I like to have deep, trusting, intimate relationships with my test equipment. I never want it to let me down.
I know exactly where you're coming from, Doug.
Yeah. Yeah.
You just want to be able to have a strong
I
relationship
want
there.
something
You
that's never going to
trust.
lie to me.
Yeah, no
Faithful.
lying. Yeah,
Faithful.
Faithful. And so my solution to that is, and like I said, I don't have enough experience with the low end, the really low cost stuff. But what I'm always doing in my lab is, does this instrument give me the same answer as this one? And if they agree, then I'm going to go, yeah, we're probably good. If all of a sudden I find that one of them seems to be out of kilter, it's like, okay, I need to do some checking, see if this thing's really accurate. But most of the stuff is such high quality.
But there's a saying in the world, a person with 1 watch knows what time it is. Someone with 2 is never quite sure. So if the 2 differ, which one do you believe?
Well, you need 5.
You need
5 watches,
You-
and chances are only one is out of line.
You
The
either
other
need
4
one that's been back to that volt in Boulder
Yeah.
at NIST, or you need multiples.
and then go back to the all measurements have error in them. It's just a matter of how much, right?
Yeah.
So, okay, a little bit more on scopes. There's a lot of cool stuff happening in oscilloscopes. And in test equipment in general. And so obviously, they're always putting in new features, trying to make it cooler, better, or whatever. So we talked about bandwidth, number of channels, memory depth. Display size is really a factor now. You know, as displays become more affordable, they're putting bigger displays in, which gives you a better picture. The waveform generator I talked about, logic channels, part of the mixed signal oscilloscope. They've got digital voltmeter features, frequency counter features, serial protocol decode, and then one of this fast Fourier transform analysis that you've got all the time domain data. Let's go ahead and apply a Fourier transform to it and take a look at it in the frequency domain. So a lot of capability being added into these. Yeah.
Are there any scopes that have an external display option that you could use, say, a computer monitor?
Yeah. They'll put for a while it was VGA. I think it's probably HDMI coming out the back now, but yeah, you can add external monitors. No surprise, it tends to be on a little bit more expensive scopes, right? It's maybe not the absolute lowest cost. Okay, a couple other scope options out there. And there's a lot of things going on, but I came across this bit scope micro, which it's one of these things where you attach it to your computer and you run an application on your computer and it controls it. So it's really compact and portable. And you can imagine students using this sort of thing, right? You could have your own little mini lab. It's pretty low performance. So it's 20 megahertz bandwidth, 2 analog channels, 6 digital channels. So it's got that mixed signal scope thing. It's got a waveform generator in there. And it's $165. So it's a pretty cool little device. And I just chose one of those from Bitscope. They've got, I think, 4 or 5 different models. And then I came across this thing, the Digilent Analog Discovery 2. It really is aimed kind of at the student, because it's kind of a electronic measurement lab. Not super high performance, 30 megahertz bandwidth on the scope, 2 channels. It's got 2 channels of function generator in it, 16 channel logic analyzer, 16 channel pattern generator. So that's a device that puts out logic levels, right? You could stimulate your circuit with that pattern generator, with digital logic. Voltmeter, network analyzer. Well, it's kind of a network analyzer. It's a basic put a sine wave out and then measure the sine wave response. You get the Bode plot from that, right? Spectrum analyzer, I think that's just an FFT function. Lots of good stuff for $400. Anybody have one of those? You guys, do you like it? Use it? Be careful. Oh man. So Greg's saying, be careful where you probe because he touched high voltage and blew it up. And then, okay, what about analog scopes? I say, sure, why not? Lots of good used gear out there. I don't know what they even go for on eBay. Frankly, they should be almost free, right? They're missing the modern digital features. One of the things you don't even think about anymore on a digital scope, typically the trigger point is in the center of the display and you're seeing what the waveform is doing ahead of that trigger point because you got the digital storage advantage there. And so it's really nice to be able to see what's going on. Analog can't do that, right? The trigger happens and then here comes the waveform. But they're really, you can make lots of great measurements with them. So that's certainly an option. Yeah.
I went to, people were selling them, showing them anywhere from $50 to $100 and they weren't moving.
Yeah. Because you got that Handtech digital scope at $250. It's like, how much am I going to spend for an analog scope. And of course, the analog tubes are inherently long, right? So as soon as you get an analog scope, it's probably at least that deep. And the digital ones now are, really shallow. So other questions?
Yeah, a question, going back to the XY presentation. It used to be in the old days that Y had good bandwidth and X did not. What's the situation now with digital scopes?
Okay, thanks, Larry. Good question. I think they're equivalent these days because they're basically just taking the inputs and running them into the same front end and sampling system. Back in the analog scopes, there was, they basically had to use the time-based system to accomplish that, and that was typically lower performance.
Thank you.
We could do a whole technical presentation on the beauty of XY mode as applied to modern electronics. So somebody can do that. Other questions? It really is a rich topic. It's kind of, there's a story behind that too. I won't go into that. Okay. All right, are we back? Okay, so now we'll talk about VNAs and SAs a bit, mostly VNA. And we should be wrapped up about 11:30-ish. And we can still take discussion, questions, whatever. Thanks for the great questions. Okay, so back to this chart. So now we're, if we're talking about VNAs, we're definitely into this RF world. Maybe it goes down and covers the audio range, maybe not, depends on the particular product. And it certainly goes way up into the RF range, 3 gigahertz, or certainly could be a lot higher than that. So here's kind of your classic vector network analyzer setup. You bought a big box. This one says what? It says Agilent Technologies on it. So the picture's a few years old, but it could say HP, it could say Anritsu or Tech or whatever. And the basic idea is the VNA provides a signal source, delivers a sine wave typically to the device under test. So we got that hooked up out here. And then the output of the device goes back to the VNA, and it can check all kinds of parameters on that network. So we would call this a 2-port measurement because the device has 2 ports, and the VNA has two inputs to handle that. There are other configurations. You can buy, many ports, many port VNAs if you need it and have the cash to buy one. And it used to be, these things were all expensive. They're like, probably started at $10,000 and went up from there, and maybe have like a, $100,000 or more in a VNA. And so we would, in the past, we'd have to talk about, well, why don't you go buy a used one on the market, and here's some good model numbers that were built, 10, 20 years ago or whatever. That's all changed now. This nano VNA is very affordable. You can make some good measurements with it, and lots of people are buying them. In fact, who's got a nano VNA or something pretty darn close to it? So we got like 4 people in the room here. So a couple of things on specs. There are many versions of this design. So that's the good news and bad news of this world. Most of it is open source. People are publishing their schematics and their software. And then other people are iterating on top of that. They go, oh, I like what you did here, but I'm gonna add this new thing. And so I didn't even attempt to try and come up with all the different models of this thing because there are so many of them, and it's always changing. So one of the advantages of that is there's a lot of innovation going on, and so these things keep getting better. But I kind of focused in on the most common lower cost one. It's like $60 from Amazon. Got a pretty small display. In fact, I'll go ahead and let's see. I don't know, Chris, can we zoom in on this? Or you want me to come out there? So it's a pretty small device. Let's see, let me get rid of yeah, you can see it there. Pretty small device. A little bit hard to read sometimes. And it does have a touch screen, and the touch screen is a little touchy. It's just small. In fact, they ship a little stylus with it. So you can use your little stylus to poke on it. But it's got the 2 SMA connectors out here. So it'll do basic 2-port measurements. So I'm gonna pass this guy around. I'm gonna put it in the box so you can see all the gizmos that come with it, but don't tip this over or we'll have a mess on the floor. Okay. Yeah, back to the screen. Whoops. Let's see, frequency range, 10 kilohertz to 1.5 gigahertz. And then it's not, I got some basic specs up here. It's really good up to 300 megahertz, does 70 dB kind of measurements for, I think both reflection and transmission, 60 dB above, up into 900 megahertz. And then it's only 40 dB up at a gig, which, okay, if you compare that to like state of the art Keysight or Anritsu, Rohde and Schwartz kind of equipment, these are kind of poor specs. They're not that great. But for ham radio use for $60, pretty darn good, right? Has a USB interface. In fact, it's Type C. And it ships with a bunch of accessories, a couple of cables and these calibration devices we'll talk about in a minute. A lot of different variations on that. Here's one that's got a little bit bigger display, and they put end connectors on it instead of the SMA. And then I just pulled this off of one of the major, more prolific distributors on the web, and they're showing, all kinds of different variations. So like this one has pretty big display, Nano VNA F, and then they got the smaller ones there. So lots of choices. So that means the disadvantage is buy carefully. You really, when you find one you think you want, you need to read the specs very carefully. One time I ordered a Nano VNA, and it showed up and it was just the PC board and no case. And I go, how did I miss that? It's like, and the description was accurate. I went back and looked on Amazon. It said it's just the board, not the case, but somehow I missed it. So don't do that. And, okay, so I can complain about the small display, but all these little gizmos have software that either comes with it or somebody has created on the web. So this particular one's called Nano VNA Saver software. And so now you can like in a bench environment, you set your little cute little device there, hook it to your computer, and now you use the software to make your measurements much more friendly in my opinion. Okay, here's another one. Actually, I bought this one way before the Nano VNAs were popular. This is called a Mini VNA, Mini VNA Pro. Now it's quite a bit more expensive, $550, and it only goes to 200 megahertz, but the specs are a lot better. So dynamic range is 90 dB in transmission, 50 dB for reflection, but its basic functionality is very similar to the Nano VNA. So I'll pass this one around as well. There are just lots of models out there, right? There are a lot of things to choose from. The Nano VNA is getting all the attention, but there are others available. It also has its own software. So this is the Mini VNA software. And this particular measurement is an antenna measurement. It's measuring return loss and SWR. The over on the right is the SWR scale, and this is the SWR plot. You see it goes down to 1. And then up here is return loss. So it's dipping in the same place as the SWR graph.
Hey, Bob, you may be getting to this in a future slide, but like on the Nano VNAs, it said there it could measure S21 and S11. Do any of them have the dual plot modes like the Keysights and that you can do at the same
I
time?
haven't found any in the low price region. And yeah, we will go a little deeper on that.
I'll hold the question.
And then here's an interesting one that my buddy Chip pointed out, K0CHP. He said, hey, I found this. Now it's quite a bit more expensive. It's $200, but the Mini 1300 did what I thought the Nano VNA needed to do. I thought the Nano VNA really is a VNA. It presents everything in terms of S11, S21, blah, blah, blah. This thing, they actually call it an antenna analyzer. And if you look at the different apps that are available, they've done a nice job of making this an antenna analyzer first. And I think it'll do pretty much everything the Nano VNA will do. So I think it's maybe best of both worlds, at a higher price. This one also is being innovated on. So people are coming out with different versions based on that design. Here's a close up to give you an idea. This is it. It can do the swept response stuff, but it also has a single frequency mode. And so here it's dialed in on 146 megahertz, and it's giving you all the information, has a little Smith chart and all that. It also has that TDR mode in there. It's pretty nice. It's got the connector is an N connector, and then it has an SMA for its second connector. So if you're using it as a antenna analyzer, you just stay on the N connector. But if you do more network measurements, you use the SMA. Okay. Now we're going to talk S parameters, because one of the issues with VNAs, it takes you into the world of scattering parameters. And so you'll hear things like Doug just said, what about S11 and S21? So I'm going to give you a quick tour through S parameters, and then I'm going to tell you the 2 things you need to remember. So we talk about 2-port networks, port 1, port 2. We have a V sub I1 is the incident voltage on port 1. VR1, sub R1 is the reflection off of that. And then we have the same thing over here on port 2. So the defining equations for S parameters are down below. And it basically says it's defined as the voltage off of the reflected voltage off of one of the ports equals S11 times the incident voltage on that port, and then plus S12 times the incident voltage on the other port. So, you know, if you think about it in the general case, things happening over here can affect that other port. Things happening on port 1 can affect port 2. So you got to have four parameters to take that all into account. And those are the S parameters. So S11 is called the input reflection coefficient. S21 is the forward transmission coefficient. So we've kind of assumed that the port 2 is the output. So and the subscripts are set up for S21 means what's happening at port 2 based on the stimulus on port 1. That's kind of how the terminology works. So forward transmission coefficient, S12 is the reverse transmission coefficient. And then S22 is just at the output port, the reflection coefficient at the output. And so you go, okay, this is where the audience goes. One third of them says, oh, I've seen all this before. And the other third says, that's a lot of stuff. And then the last third says, I don't really care. I don't know what he's talking about. But anyway, it's good to kind of have this in your brain, because as you look at the nano VNA and stuff, they'll use this terminology to describe things. But really, here's the two things to remember. On port 1, there S11 is the reflection measurement on port 1, and S21 is the transmission measurement. And the nano VNA, and really, I think all of these low-cost VNAs only measure these two things. They measure the reflection, and then they measure transmission. And as Doug alluded to, you know, professional grade VNA is going to have the ability to measure all four S parameters simultaneously. But really, for hobby and ham use, this is just fine. Really, if you have reflection and transmission, it's pretty darn good. So what does that mean? Here's how that turns into reality with your nano VNA. The nano VNA has two ports or two connectors, and it labels them channel 0 and channel 1. And on this diagram, it's showing the transmission. Well, it's showing both measurements. So you hook up channel 0 to port 1, and then port 2 is connected to channel 1. Oops. And so in this configuration, I can measure the reflection parameters on port 1. So I could measure its impedance, its SWR, its reflection coefficient, all that kind of stuff. And I can measure the transmission through this device. So if this was some kind of filter or amplifier or whatever, the channel 0 puts a signal into port 1, and then channel 1 measures what's coming out of port 2. And so we can do the S21 transmission measurement. Make sense? Almost. This channel 0. I'm sorry, ask that again. Yeah, that's correct. Thanks. He's not on a microphone, so he's just just confirming that port 1 is the input to the 2-port network and port 2 is the output. Okay, so how might we actually use this? If I'm making antenna measurements, I just hook it up to channel 0. And I'm going to make a reflection measurement on that antenna. But you know, the reflection measurement can be shown in many formats. I can choose reflection coefficient, SWR, return loss, whatever I want, but it's a reflection measurement. Now, another thing that the VNA approach brings into our world that you may not be familiar with is the need to calibrate. And so here's a close-up of the nano VNA. I pulled this off of a website, and if you see as we're passing that thing around, some accessories ship with it. There is a little SMA connector called an open. There's a short and a load. So the load's going to be 50 ohms. A short is going to be a short, zero ohms. And an open's kind of funny because you go, why do I need an open? Can't I just leave the connector off? Yeah, you probably can. But what the open does is gives a more controlled open impedance that makes for a better cal. So it's a calibrated open, which, you know, if you think about it, if you just open a connector, what do you really got there? But if you put the calibrated open on, you know exactly what's at that port. So those come with it. And so we have to do a calibration step, and it's not real difficult, but you have to be aware of it and you have to do it. So if I'm doing a reflection measurement, so I'm only going to use channel 0, then I go into my menu system on the nano VNA, and you go to calibration. You say it'll show you things like you know, connect your load. So you put the load on there on channel 0, and you press that's my load, and so it goes out and it measures. It takes, I don't know, 30 seconds or something. It has to go do some sweeps to measure that load. Then you take the load off, set that aside. You put the short on, and you go measure the short, and it goes off and do that. And then okay, then you take that off and you put the calibrated open on, and press open, and it measures that. And so that is a very standard and common technique on VNAs that provides you the most accurate measurement, because it's going to take all that information and it's going to correct for any errors in the system. Basically assumes these things are perfect, right? And so in the world of big test equipment, these calibration kits can be really expensive, right? And they're, you know, guarded with, people have like their own special cal kit they won't let anybody else use because they don't want to lose it or have it get screwed up and all that. This is less critical, but still an important step in using a nano VNA. So that's the reflection thing. Yeah, question.
Is that every use? Every use you calculate before you use it?
Oh, good question. Thank you. So once you do the calibration, you want to store that in, they've got, I think 5 memory locations you can store your cal. And probably in an ideal world, you'd probably do this every time you use the VNA, but it's not going to drift that much. So if you like used it one day and came back the second day, you probably don't have to recalibrate every time.
Hey, Bob,
Yeah.
one of the things is, yes, a cal kit is like a toothbrush. It's very personal, and I
You're
want to know.
personal with your cal kit.
Yeah, I want to know who's abused
Where's
it,
it been?
and is it really staying in?
Yeah.
Is it really in calibration? But one of the other pieces is you may calibrate your instrument from 400 to 500 megahertz, and the sweeping and the resolution will be different than if you calibrate from 30 megahertz to 3 gigahertz. So you may have multiple cals that you're going to store. As long as you know, hey, I'm going to a UHF thing, I want to look from 400 to 500. The other piece is, it'll be very important, your cables that you put on this. And you can put those cal kits at the end of your cable and adjust for that. And I'm assuming I can do that on my HP Agilent key sites. I'm assuming we could do that with the nano VNAs, and you can actually compensate for the loss of those
You're
cables.
2 slides ahead of me.
Okay, I'm
Excellent
gonna shut
point.
up now.
Let's do the, want to emphasize what he said about the different cals. So if I'm just kind of goofing around with the VNA, I'd probably cal the whole frequency range and say, okay, that's pretty good. But if I zoomed in on, I'm working on 440 something megahertz antenna, I'd probably set up the VNA for, 430 to 460 megahertz. And I'll go ahead and do a cal over that range and save it, because that'll give me a much finer look at it'll give me a better measurement result. So you may end up saving a couple different cals going on. Yeah.
But if you're going to be testing your antenna, you want to look at the entire system. So wouldn't you cal on the nano VNA at that point in time, because you're actually testing your coax and all that. You don't want to eliminate any of that.
Well, you might
any
do
of the
both,
coax.
right? You might say, hey, I want to look at the whole frequency range, see what's going on. But then when I'm really looking at the SWR of a antenna, I zoom in on the frequency I expect to be operating, right? So you might end up with like 2 cals saved, and you switch back and forth. Yeah. Okay, so that's the reflection. And then on the transmission, see, I'm not doing reflection measurements over here. I'm only doing on channel 1. It's a 2-step process. It's an open, and then I hook up a little cable that is a through. And so that's going to be the most important calibration, because it'll take out any variation in, like, if the signal source has some level variation, the VNA is going to measure that, and it's going to remove that from the end measurement. So that's the transmission thing. And then Doug's other point. So why are you doing all this? Well, in a lot of cases, the cables can get in the way of making a good measurement, especially the higher you go in frequency, the more cable loss this is. So if you have significant cables, or maybe some adapters that you can't get out of the system, you just have to do adapting to get things hooked up right, you go ahead and perform the calibration out here at we call it the measurement plane. So like normally we'd say the measurement plane's back here because we're just connected to those inputs, but we can come out here and make this our measurement plane, and we attach the open short load through here, and it'll remove the effects of the cable. So it's very, very powerful. Okay, here's some real measurements. This is an M squared 2-meter antenna, 9 element. And I use this portable all the time for VHF contesting. And but here's some measurements of this antenna. These were actually made with the mini VNA Pro, but the same principles apply to any of the VNAs. So here I've set it up. I looked over 140 megahertz to must be about 148. It's labeled at 147.5. And so I'm showing SWR and return loss. So the top, I think this is actually the same data I showed on the app about 8 slides back, but the top is return loss. You see that it dips down to about 35 dB return loss, which is pretty good. This is going to be the best resonance for that antenna. And then here's SWR. SWR is over the axis is over here, and it looks like it's actually tuned a little bit low for ham use, right? This is 145. So it's probably just below 144 megahertz. I would expect it to be tuned low because it's really intended for single sideband, the low end of the band, but it's probably even lower than expected. See, so again, you can see the whole picture of what's going on in my antenna system. You know, where's it tuned to? What's the SWR return loss, that sort of thing. I can also say, okay, I want to look at, this is impedance. So it's the magnitude of the impedance on the same frequency scale. So no surprise in the spot where the SWR was pretty low, we're right around 50 ohm impedance, right? You see the scale on the left side. That's about 50 ohms. And then as I move away from there, it kind of drifts up to a little over 100 ohms. That's still in the ham band, but significantly higher impedance. I can look at, this is R and X, okay? So it's the impedance, the real part of the impedance and the reactive part of the impedance. And
One comment, Bob, about resonance of an antenna.
Yeah.
Resonance of an antenna is not necessarily related to whether that antenna is actually going to radiate. So you need to know that the design of your antenna is good in the first place. You'll know that it's resonant. You may not know, I mean, like a dummy load is resonant everywhere, but that doesn't mean that it radiates. So the quality of your antenna also goes into that factor.
yeah, so that's a really good point. I think of it this way. It's, you know, this was a commercially made antenna that I assembled, and as long as I followed the instructions, I'm going to have pretty good confidence that, you know, a good design, assembled correctly, and measured for SWR. Okay, I've got confidence that's probably working pretty well. But if I did something like just got a bunch of elements, aluminum elements, invented the K0NR antenna, some new quad cubical reverse osmosis Yagi antenna, and I assemble that and I find out the SWR is awesome, it really doesn't mean anything. Yeah. Okay, so here's measuring R and X. So let's see, where are we? We are, so R is over on that axis. So this is R here, kind of hanging around 50 ohms. Then it peaks up towards the edges. And then X, there's very little reactance at the resonant point. And then it gets a little bit of reactance going higher in frequency, then it takes a big dip there. So it lines up with what the SWR was telling us as well. Okay, and then transmission measurement. So again, using the mini VNA, this is a bandpass filter made by DCI it's about this big, and it's got probably, I think it probably has 4 or 5 stages of filtering. It's intended to protect your 2-meter transmitter from other signals. So you can get the best performance. So if you had two stations on the air close by, right, you could use that to protect it. And so did a transmission measurement. So it's going to be using both ports. And I calibrated it pretty carefully. You'll see in the pass band up here, it's got maybe not even a dB of loss. So it's pretty low loss in the pass band. And then it has nice skirts that come down on either side, rejecting adjacent frequencies. And then here's a zoom out picture to see, you know, does it keep protecting me against other potential radio signals? Sure enough, the skirts keep coming way down to like, what is that, minus 65 dB on the high side, and over here it's down to minus 75. And then you see it getting noisy down here. So this is where we're reaching the limitations of the measurement, right? We don't really know what's going on down here, but it's a pretty nice filter. Okay, questions on VNAs? Okay, I think we're wearing them down. Yeah. Yeah, question is, well, go ahead.
DNA, as far as connecting to an antenna and blowing it up?
That's a really good question, and I think the answer is yes. These are pretty sensitive devices, so. In fact, I was just talking to somebody at dinner last night and he said, yeah, I had an nano VNA and then I blew it up one day because I connected it up to something I shouldn't have. So yeah, these are pretty sensitive devices.
Little oscilloscope was about this big, except the maximum voltage you could put into it is 5 volt. Did exactly that to it.
Okay, so let's do a little bit on spectrum analyzers. So again, we're in that realm where it's RF measurements and its frequency domain is the major focus. So I remember thinking when the nano VNA came out, I said, that's pretty cool, but I really just want a spectrum analyzer. And sure enough, yeah, I know. And so out came the tiny SA. I guess it's not a nano, it's a tiny. And yeah, can we do the zoom in here? Oh, that's a pretty good picture on the, yeah, so here's the tiny SA. I'll say maybe this one isn't quite as mature. For example, it's got a low input and a high input. So, which is low frequency and high frequency. I think the low frequency goes up to about 300 megahertz and the other input goes up to whatever I said a minute ago, 950. Yeah. 950, 960 megahertz. So you got that to be concerned about. There is some signal generator capability in here. You can turn these ports into a signal generator. Just like the nano VNA, there's a lot of innovation going on. So people are taking this design and improving on it. And there's all kinds of variations coming out. So I think over time, this is just going to keep getting better and better. Let's go back to the chart and I'll pass this around. You can see what accessories come with it. Don't tip over the box or we'll have a mess. Okay, yeah, low input goes to 350, high input goes to 960. The resolution bandwidth is how it's basically the frequency resolution limit. How finely can I look at the spectral components of a signal? It goes down to 6 kilohertz. That's actually not that tight, right? That's kind of big. So that'd be maybe a limitation. Well, that is a limitation of this device. But again, for a lot of the stuff we do, that's probably just fine. Dynamic range, they say, is about 70 dB, which actually not bad for a low-cost device. There is a signal generator mode, displays about 2.8 inches and $70 for that one. You notice they do have this is a waterfall display down here, so you can do this. Take subsequent repeating measurements and have them show up as a waterfall. And then in terms of practical measurements, what's being shown here is a harmonic distortion measurement. You can see this is the fundamental, and I forget what frequency that's at. I think it's around 50 megahertz. And then at integer multiples from that, you can see the harmonic content. The vertical is 10 dB per division. So this third harmonic is pretty high. It's maybe 12 dB below the fundamental. So some people would say that's probably a Baofeng radio, but I wouldn't say that. Some people might. And then even the fifth harmonic is pretty high. So anyway, that's one practical measurement you can make with these things. Just like the Nano VNA, they have software apps that go with it. So you're not limited by the display. You can go run your computer and look at the data that way. And then again, this one you can see harmonic. This is a different measurement. You can see harmonic distortion in there. That's interesting. Looks like the second harmonic is, usually it's the odd harmonics that are the bad boys, right? This one, I think that's the second harmonic there. No, that's the fundamental. Sorry. That's the fundamental. This is the second harmonic. And third harmonic. And then the other thing to note is you've got all these spurs down here below. And they're about, let's see, the fundamentals there. So let's call that 10, 20. Yeah, they're over 80. Most of them are over 80 dB down. That's not. No, that can't be right. Let's see, this is. I'm having trouble reading the graticule, but let's call that 60 dB down. There are spurs present in this signal, right? So that's the kind of thing you might want to look at it from time to time. It's like, okay, how clean is this transmitter? Or how clean is this signal source? And that's what a spectrum analyzer is really good at, right? If you tried to do this with an oscilloscope, you're just going to see a big sine wave, right? You're not going to be able to see any kind of detail like this. So some options. Regal, again, has a pretty cost-effective spectrum analyzer, about $1,000. People seem pretty happy with it. Goes up to 1.5 gigahertz. So that's more of a, bench kind of product. Certainly a lot higher price than the tiny SA, but they didn't spec dynamic range, but the DANL displayed average noise level was quite good. And then their res bandwidth, the resolution bandwidth, the frequency resolution goes down to 10 hertz. So you can really zoom in and look at the fine details of a signal, the spectral content of a signal. And then there's a lot of used gear out there. I've got one of these 8590. It's old. I trust it. I have a relationship with it now. Good piece, good product. But I don't know what looked like on eBay. They were still going for like $500, something like that. Maybe less if you looked around. And I love a lot of the old HP gear because I sort of grew up with it, so to speak, and trust it, know it, and all that. The big downside is, I might have this and then the CRT might quit on me. And now I'm, into either buying something else or figuring out how to fix it. And it's kind of always a risk with older equipment. Yeah, it's probably 15K. Yeah. And sweep, one comment over here is the sweep is significant faster.
Hey, Bob.
Yeah, there's a lot to love about that old stuff.
Yeah, I think one thing, to point out with the spectrum analyzer is, it does have a broad frequency range. So it's got a real wide receiver, that you've got to be careful in the signals that you put in there. You may want to use a filter. Otherwise, the instrument, you may be seeing intermod and stuff generated within the instrument from overload.
Yeah, that's a good point. Basically, this is an imperfect device, same as, all these spectrum analyzers we've been talking about. And so one phenomena is if you drive it too hard on the input, you can create distortion in the front end of the analyzer that you start thinking, oh, that's in my signal, it's in my transmitter. It's not, may not really be there, right? So you always have to be careful. Yeah, Jeff.
Yeah, another thing about used gear like this is you don't know how well calibrated it is.
Right.
And what is it going to cost you to get it calibrated, depending on what you're going to use it for. So you have to take that into consideration. I mean, if it's going to cost you, $1,000 or something to send it out to have it called, then you
That's
have
a
to
really
take
good
that
point.
into
Yeah,
consideration.
that's not, it could easily cost you that much to
Yeah.
get
But
good
its
cal.
calibration is probably better than a micro spectrum analyzer that you buy for $100. So.
Right, right.
Yeah. And I think that's where you differentiate between hobbyist stuff versus, if you have equipment that you are using professionally that is supposed to be have a guaranteed measurement result, then you need to be thinking calibration. And so that becomes kind of like a maintenance cost, right? You have to calibrate it every once in a while. Okay, a couple other things. So the other thing that's really popular in the low cost gizmos are all these software defined radios. And if you think about it, a software defined radio kind of shows you all the spectrum that's connected to its input. So it can function as a spectrum analyzer in many ways. Now, the very cheapest one tends to be things like this, the RTL SDR, about $20. They're all the low cost ones are based on this tuner IC. And so they have a lot in common, but they have a cutoff frequency that's not real low. This one's 25 megahertz and it goes all the way to 1.7 gig, but it's $20. Good Lord. And then here's a little bit better one. This is the SDR Play. People seem really happy with this. I'll go ahead and pass it around. It's $99 at HRO. You can drive over there this morning. 14-bit A to D converter, covers down to 1 kilohertz, up to 2 gig. Let's see. Excellent dynamic range. Works with there's a whole bunch of SDR software out there. You probably had a presentation on SDR stuff here, didn't you? Yeah. And if you look at the block diagram, they actually went and they put a bunch of filtering in there so they could, again, this whole issue of strong signals come in, overload the receiver, can cause you to have poor results. Well, they've done a pretty decent job of filtering, and then they also the frequency stability is pretty good too. They put a crystal oscillator in there, I think. And so here's the standard software that comes with it, SDR Uno, but there's others out there, right? Because they all suck data in that IQ format, and so there's a bunch of choices there. But who's got some kind of SDR they're playing with? Yeah, lots of people. They're pretty cool for the money. And then they did come out with this, which I found pretty interesting. Somebody, again, lots of innovation going on, crafted a spectrum analyzer app that uses the SDR, but kind of presents it in a more spectrum analyzer format, in terms of the controls and such mostly, because I don't know, we don't see, I've always find the user interface model on SDRs is kind of wonky. It's like you're in there adjusting their block diagram parameters to get the answer you want. Whereas This software was set up to act more like a spectrum analyzer. I think it does a pretty good job. Okay, so that's SA stuff. I did want to comment a little bit about connecting to transmitters. Because if you do want to use a spectrum analyzer or even a scope to connect to your transmitter, you need to take some care. You know, typically you got 100 watts coming out of that transmitter. So one easy way to do it is get a power attenuator. So here we've got power attenuator with big heat sink on it, and we feed that into the spectrum analyzer. Now this spectrum analyzer was rated as 1 watt damage level, right? I probably don't want to get close to 1 watt. I probably want to be below that. So let's see, 100 watt transmitter. How much attenuation do I need? 10 dB is a factor of 10 in power, right? So 100 watts with 10 dB would get me down to 10 watts. 20 dB takes me down to 1 watt. Yeah, maybe I want that 30 dB attenuator. I'd get down to 0.1 watt. Stay way below the damage level on that device. Now, if you got a kilowatt amplifier, it's another factor of 10. So you're going to need more attenuation. You're also going to need an attenuator that can handle a kilowatt into it. So that's some serious stuff. Now, the other method is to use an RF sampler. And the advantage of this, of course, you could just leave it in line and hook up your antenna or maybe a dummy load, depending on what you're doing. And so you could sort of monitor over the air, and you can buy these. They're manufactured for just that purpose. I actually made one. I just put a few resistors. I put a through circuit to pass it through, and then I tapped off with a couple of resistors as a voltage divider. It's honestly not very well calibrated, but it gives me the ability to see what's going on. So you could, and so the through, you want zero loss on the through path, and tap off some signal and feed it to a spectrum analyzer or your oscilloscope. Again, got to be concerned about signal level. Usually there's quite a bit of attenuation here, like 20, 30 dB. It may be.
Hey, Bob, can I share some advice that an Elmer of mine gave me?
Yes.
He said, always read the yellow sticker there right by your end connector on your spectrum analyzer. And that'll probably say like 1 watt, but that may or may not be continuous. That may be intermittent. A lot of these instruments will take 2 watts for a minute and then 1 watt continuous. So that's something to keep in mind. He also pointed out to me that just because it has a type N connector and I'm in your Yaesu up here, it doesn't have a type N, but you've drawn it as that. Just because that's a type N and your spectrum analyzer is a type N doesn't mean they were meant to go together. Always look at the label. And I can honestly say that I have only plugged a 100 watt radio into a service monitor that I thought was rated at 100 watts. And then I found out that this was the special model and the sticker said 4 watts. I've only blown up an instrument once in my career.
Interesting kind of special.
So it happens to all of us. And yes, I was very red-faced when I had to bring it back and go, I blew it up. So
it's like
always check the
destroying
labels.
your best friend, right? You blew up your spectrum analyzer.
I felt like I ran over my puppy dog with my car in the parking lot. I felt terrible, but it happens. But if you look at the stickers and you always say, what is the maximum power this thing can put out? And some people said, well, I took my Yaesu and I turned the power all the way down to 0. But then we had some radios that would initially spike to full power and the power control would bring it back. And that will blow up your spectrum analyzer. Some people have said, well, I'm testing a trunked radio, a police radio, and I'm not going to transmit. I took the microphone off. Unfortunately, when you turn the radio on, it says, I need to check in with the system, and puts full power into the instrument. So always be sure.
Yeah, that's really good. One of the things I noticed over the years is that like I'd say high quality spectrum analyzers, signal generators and such, they're pretty, they do what they can to make them robust and not blow up easily, but you can blow them up. The service monitors or something they know is going to be connected to a transceiver. They usually put more protection in and relays that open and stuff,
Yes.
trying to save that poor device from the mistake of the operator.
Well, in these days, most commercial service monitors that we'll buy, grant you, these are about a $30,000 instrument. They'll be labeled for 60 watts continuous, but they will handle 100 plus temporarily. And what happens is that load, there's basically a dummy load or an attenuator on the front end. So they're looking for and adjusting it. And when they see this is 100 watts intermittent, and you're at about 150 watts, within quarter of a second, that relay opens up and protects the instrument and just dumps it all into the dummy load until
Yeah.
that heats up and blows up.
Yeah.
Unless you've got an instrument that's high sensitivity and set down to 4 watts, and I didn't notice the sticker.
Yeah. Yeah. Okay. That's all I got. What you got for questions? Yeah.
If you're not worried about measuring amplitude with the spectrum analyzer on your transmitter, how about just putting an antenna on the spectrum analyzer input? I've tried that.
Yeah. In fact, if you're, I don't know if you noticed in the tiny SA that went around, there's actually a little, they ship it with a little antenna. And so, yeah, that's a common usage, right? You can take any old antenna, usually just a telescopic something or other, and put it on with a BNC connector, put it on the input of your spectrum analyzer. You can monitor, you can pick up signals over the air, right? It's just, you won't be calibrated, right? You don't really know what the characteristics of that antenna are. So if you said, I'm going to do a harmonic measurement, and you saw that the harmonic was, 50 dB down, was it really 50 or is it 45 or 50? You don't really know. It's not that repeatable. Other questions? I think we're good.
Okay, no more questions, and thank you, Bob, and I think that's worthy of a round of applause.
Thank you so much.
Left-handed, right?
Yeah.
Thanks, everybody, again for being here. Make sure you take all your stuff out, because once you walk out, you're not going to be able to get back in, once we leave. So grab all your stuff, clean up around. Once again, I did want to mention earlier that on Giving Tuesday, there were quite a lot of donations that did come in, and we very much appreciate it. If there's anybody here or on the Zoom call that donated, thank you very much appreciated. And again, keep those cards and letters coming in. And of course, we're always looking for donations. So we continue we're upgrading our network. We're putting in a lot more microwave links. And for those that aren't aware, we have built what we refer to as a standalone network. The internet goes down, if the commercial power goes down, our network is survivable. And it's all linked together using amateur radio microwave. So hopefully in an emergency, when all else fails, we're still going to be there to support the amateur radio community and the citizens of Colorado. So we very much appreciate your support. Any other further questions about Rocky Mountain Ham or anything else? If not, happy holidays.
Also, I just wanted to add a word of thanks to our AV team. So Chris Keller, John Maxwell, Mark Skelton, and Dave Mesarowski, who ran the class today. Appreciate all of your efforts and coming in yesterday to set everything up. And we usually gather for lunch. So if you're interested in, anybody interested in going to lunch at La Fogata after this meeting, raise your hand so I can see. 1, 2. Who else for lunch? 3, 4, so maybe about half a dozen. Okay. Thank you very much, Bob. Very
All
much
right,
appreciated.
thank you.